Right now, as you are listening to this, you are forgetting something, not consciously, a name you will never need again, a moment from Tuesday, a face from a room you walked through once. And here is the strange part, that forgetting is not nothing. It has a price, paid in heat, in a currency physics can actually measure, and the amount has been calculated and then confirmed in a laboratory. Losing a memory warms the room. It is an almost unimaginably small amount of warmth, and it is not zero, and it is written permanently into the accounts of the universe, which turns out to matter far more than it sounds, because when physicists went looking for the thing that gives time its direction, they did not find it in the stars and they did not find it in the equations, they found it in the bookkeeping. So what happens when somebody learns to keep the books differently? Make yourself comfortable, subscribe if you haven't already, and stay with us, because by the end of tonight you will know exactly what a group of physicists managed to turn around this year, what they did not, and whether this is really the breakthrough everyone said it was. Let's dive in. Part 1. The paper that should not be possible. In February of 2026, a physics journal published a sentence that should not have been publishable. The journal was Physical Review X, which is not a fringe outlet. It is one of the most selective open-access journals in the field, the kind of place where a paper arrives only after referees have spent a long time trying and failing to find the hole in it. The paper appeared in volume 16. Its title was 4 words long, and the 4 words were these: Reshaping the Quantum Arrow of Time. Now, arrows of time are not supposed to be reshapeable. That is more or less the definition. The arrow of time is the name physicists give to the single most reliable fact anyone has ever noticed about being alive, which is that things happen in an order, and the order does not run the other way. Cups fall off tables and shatter. They do not gather themselves up off the floor and leap back onto the table, reassembling as they go. Coffee cools. It does not spontaneously reheat by drawing warmth out of the room. You remember your childhood and you do not remember next Thursday. Whatever else is uncertain about the universe, the direction of time has always seemed like the one thing you could lean on. So a paper claiming to reshape it is either wrong, or it is very carefully saying something narrower than it sounds, or it is one of the more important things published this decade. And the interesting part, the part that made me want to spend the next 2 hours with you on this, is that the answer is not obviously any one of those 3. The 3 names on the paper are Luis Pedro Garcia Pintos, Yikai Liu, and Alexei Gorshkov. Garcia Pintos is a physicist at Los Alamos National Laboratory in New Mexico, which most people know for one thing it did in the 1940s and know almost nothing else about. Los Alamos today is, among other things, one of the more serious centers of quantum information research in the United States. Liu and Gorshkov come out of the joint quantum research world that clusters around the National Institute of Standards and Technology and the University of Maryland. Gorshkov in particular is a name that appears on a great many papers in quantum many-body physics, and his presence on a piece of work is a reasonable signal that the mathematics has been done properly. The paper did not appear from nowhere. It had been sitting on the public preprint server since March of 2025, nearly a year before publication, and it was substantially revised in December of that year before the journal finally ran it. That is a gap of roughly 23 months between the first public version and the final one. In quantum information theory, where preprints often go from posting to publication in a few months, 23 months means the referees pushed back, and pushed back hard, and the authors had to go away and do more work. I want to flag that now because it is going to matter later. A paper that survives that process is usually a paper whose claims have been trimmed down to exactly what the evidence supports. Then, some months after publication, the story reached the general public, and here is where it gets interesting. The headline that carried this result to most of the people who heard about it read, "Scientists make quantum time flow backward in stunning physics breakthrough." Hold those 2 sentences next to each other for a moment. The paper says, "Reshaping the Quantum Arrow of Time." The headline says, "Scientists make quantum time flow backward." Those are not paraphrases of one another. They are not even close. The first is a statement about a mathematical property of a certain kind of record. The second is a statement about the world, a claim that somewhere in a laboratory, for some brief interval, the ordinary forward flow of events was turned around and something ran the other way. I'm going to leave that gap open. I am not going to close it yet. Because how you close it turns out to be the entire question, and getting there honestly requires going a very long way around. Here is what the abstract actually says, and I want to read it slowly, because every single qualifier in it is carrying weight. The authors write that while the microscopic laws of physics are often symmetric under time reversal, most natural processes that we observe are not. The emergent asymmetry between typical and time-reverse processes is referred to as the arrow of time. In quantum physics, an arrow of time emerges when a sequence of measurements is performed on a system. And then the claim, we introduce quantum control tools that can yield dynamics more consistent with time flowing backward than forward. More consistent with, not, that flow backward. More consistent with time flowing backward than forward. That is the sentence. That is the whole result. And if you understand exactly what those 5 words mean, you understand this paper better than almost everyone who read about it. There is a second tell, and it is in the announcement that Los Alamos itself put out. The lab's own description of the work says that the tools constructed in the paper can manipulate the perceived arrow of time. Perceived, not the arrow of time, the perceived arrow of time. Institutional press offices are not famous for underselling their scientists, so when a national laboratory's communications team chooses the word perceived, somebody in that building insisted on it. And there is a third tell, which is the most revealing of all, and almost nobody noticed it because it is buried in metadata. When you post a paper to the preprint server, you choose which subject categories it belongs to. This paper is filed under 2. The first is quantum physics, which you would expect. The second is statistical mechanics. Statistical mechanics is the branch of physics that deals with heat, entropy, engines, and the behavior of large numbers of small things. It is the branch of physics that was essentially finished in the 1800s, that gets taught to undergraduates as the least glamorous subject on the syllabus, and that has nothing whatsoever to do with time travel. The authors filed their paper about the arrow of time under thermodynamics. That is not an accident, and it is not modesty. It is a statement about what kind of paper it is. There is a fourth tell, and this one is almost comic. The version of the article that reached the widest audience was tagged, by its own publisher, with a list of subject keywords. The list read, space exploration, batteries, energy and resources, thermodynamics, physics. Batteries, energy, thermodynamics. 4 of the 5 tags on an article headlined about time flowing backward are about where energy goes, and not one of the 5 mentions time at all. Even the filing clerk knew what this paper was really about. The funding tells the same story from a different direction. This work was paid for by the United States Department of Energy through its Advanced Scientific Computing Research Program, by a project at Los Alamos called Beyond Moore's Law, and by the National Science Foundation. Beyond Moore's Law is a program aimed at figuring out how to keep making computers faster once you can no longer make transistors smaller. That is applied computing money. That is money that expects, at the end of a long chain of results, a machine. Nobody funds time travel out of a computing architecture budget, so we have a paper with a title that sounds impossible, an abstract full of extremely careful qualifiers, a press release that says perceived, a subject listing that says thermodynamics, and a funding line that says build me a better computer, and then a headline that says scientists made time flow backward. Somewhere in there is the truth, and I think it is genuinely more interesting than the headline. But I cannot hand it to you yet, because the honest version of this story requires you to know something first, and the something is this. We do not know why time has a direction. I do not mean that as a poetic flourish. I mean it as a technical statement about the current condition of physics. Every fundamental equation we have, every single one, the ones that describe how planets orbit, how light propagates, how particles interact, how space-time curves, is completely indifferent to which way time runs. You can take any of them, flip the sign on the time variable, and the equation is just as satisfied as it was before. The laws do not contain a preferred direction. They have never contained one. Nobody has ever found one. And yet here you are, in a world where the cup shatters and stays shattered. That contradiction has been sitting at the base of physics for about 150 years, and every serious attempt to resolve it has ended up in the same strange place. A place where the direction of time turns out to depend not on the universe, but on what somebody is keeping track of. Which is why, when a paper comes along claiming it can reshape that direction, the first question is not whether they did it. The first question is what exactly they got their hands on. Part 2. The film that runs both ways. Let me show you the problem properly, because it is stranger than it sounds when you first hear it. Take Newton's laws of motion. They describe how objects push each other around, and they have been describing it accurately since 1687. Inside those laws there is a variable for time, and the variable appears in a very specific way. If you take Newton's equations and replace time with negative time, literally flip the sign, run the clock the other direction, the equations remain true. Every solution to the forward equations is also a solution to the backward equations. Newton's laws do not merely permit the reverse, they cannot tell the difference. The same is true of Maxwell's equations, which describe electricity, magnetism and light, written down in the 1860s. Flip the sign on time, adjust the direction of the magnetic field, and the equations hold perfectly. Light running backward is exactly as legal as light running forward. The same is true of Schrödinger's equation, the central equation of quantum mechanics, written in 1926. It is time-symmetric in the same essential way. And it is true of Einstein's field equations, which describe how mass and energy curve spacetime, published in 1915. Nothing in general relativity says which way the clock ticks. 4 sets of equations, 4 different pieces of the universe, roughly 340 years of physics between the first and the last, and not one of them contains a preference for one direction of time over the other. Let me make that concrete, because it is the kind of thing that sounds abstract until you actually picture it. Imagine a ceramic mug sitting near the edge of a kitchen table. It slides, tips, and falls. It strikes the tile floor and shatters into perhaps 40 pieces, which skitter outward across the kitchen. The sound is sharp and then it fades. This takes about half a second. You have seen it happen, or something like it, and you know exactly what it looks like. Now run the film backward. The pieces are scattered across the floor motionless. Then, without anything touching them, they begin to move. They accelerate inward toward a common point, each one on its own precise path. They arrive at that point simultaneously, edge meeting edge, and as they meet, the cracks between them close. The sound of the impact plays in reverse, a sharp report that gathers itself out of the room's ambient noise and concentrates into the moment of contact. The reassembled mug, now whole, lifts off the tile and rises toward the table, decelerating exactly as it climbs until it comes to rest on the edge with almost no velocity at all, and then it sits there. Every instinct you have says that is impossible, but go through it collision by collision, and you will not find a single violation. Take any 2 ceramic fragments at any instant in that reversed film, and check what they are doing against Newton's laws. The forces are correct. The momenta balance. Energy is conserved at every step. The sound waves converging on the impact point obey the wave equation exactly. The heat flowing out of the floor and into the fragments, giving them the kinetic energy to move, is doing nothing that the laws of mechanics forbid. Physics watches that entire film and does not object once. The universe does not know which way is forward. That is not a metaphor, and it is not a philosophical position. It is a statement about the mathematical structure of every fundamental law we have, and it creates a genuine scandal because you live in a world where the reverse film never plays. Not rarely, never. Nobody in the history of the species has watched a broken cup reassemble. So where does the difference come from? The person who first insisted that this question needed a real answer, rather than a shrug, was an Austrian physicist named Joseph Loschmidt, and the year was 1876. Loschmidt was a friend and colleague of Ludwig Boltzmann, and Boltzmann had just done something extraordinary. He had proposed that heat and temperature and pressure, all the messy, tangible properties of matter, were nothing more than the statistical behaviour of enormous numbers of molecules bouncing around. And he had gone further. He had produced an argument, now called the H-theorem, which appeared to show that a gas left to itself must become more disordered over time. Which is to say, he appeared to have derived the second law of thermodynamics, the law that gives time its direction, from the mechanics of molecules. Loschmidt read it and found the flaw immediately. His objection is one of the cleanest arguments in the history of science, and it goes like this. Suppose you have a box of gas, and it starts out ordered. All the molecules crowded into one corner, and over some interval it spreads out and becomes disordered, exactly as Boltzmann says it must. Fine. Now take that final state and reverse the velocity of every single molecule. Every one. Same positions, opposite directions. That new state is a perfectly legal state of the system. Nothing forbids it. And because the underlying mechanics are reversible, the gas will now retrace its steps exactly. It will unspread. It will gather itself back into the corner it came from. Order will increase, not decrease. And it will do so while obeying every law Boltzmann is using. So the H theorem cannot be right as stated, because the same laws that supposedly force disorder to increase also permit a state in which disorder decreases. You cannot get an asymmetric conclusion out of symmetric premises. Something has been smuggled in. This is called the reversibility objection, and Boltzmann took it seriously, and his eventual answer changed how physics thinks about everything. The answer is counting. Boltzmann's position, worked out over the following years, was that the second law is not a law in the way Newton's laws are laws. It is not a prohibition. It is a statement about odds, and the odds are so lopsided that the distinction stops mattering. Here is the reasoning. For any collection of molecules, there are a certain number of arrangements that we would describe as ordered, all the gas in one corner, and a certain number we would describe as disordered, gas spread evenly through the box. The disordered arrangements are not slightly more numerous. They are more numerous by an amount that has no useful comparison in ordinary life. Consider a single gram of ordinary matter. It contains something on the order of 10 to the 23rd particles. That is a 1 followed by 23 zeros. If you started counting those particles at 1 per second at the moment the universe began, and you were still counting today, you would have gotten through a vanishingly small fraction of the ones in a single paperclip. Now ask how many ways you can arrange that many objects. The number of possible arrangements is not 10 to the 23rd. It is vastly larger. It is a number whose number of digits is itself an astronomical quantity. Against that, the arrangements that look ordered to a human being are a rounding error on a rounding error. So a system left alone does not become disordered because a law compels it. It becomes disordered because it is wandering more or less at random through the space of available arrangements, and almost every arrangement available is a disordered one. The reversal Loschmidt described is entirely permitted. It simply requires you to hit one specific arrangement out of a number of possibilities so large that the universe has not existed long enough for it to come up by chance. That is Boltzmann's answer, and it is essentially the answer we still use. Notice what it does and does not do. It explains why disorder increases going forward. It does not explain why the past was ordered in the first place. If the reasoning is symmetric, and it is, then the same argument says the system was probably more disordered a moment ago too, which is flatly wrong, because a moment ago the cup was on the table. Boltzmann's statistics tell you which way things go from an ordered starting point. They cannot tell you why there was an ordered starting point. That hole has never been filled. Physicists have a name for the assumption they use to patch it. They call it the past hypothesis, which is a very grand phrase for the admission that we simply assume the universe started in a low-entropy state, because otherwise nothing works. It is not derived from anything, it is bolted on, and I want you to hold on to what this means for where we are going, because it is the hinge of the whole story. If the arrow of time were a law, if there were an equation somewhere that said time runs this way and not that way, then a paper claiming to reshape it would be crackpot work and we could stop here. But it is not a law. It is a bias in the odds. It is a fact about counting arrangements and about which arrangements a system happens to be wandering through. And a bias in the odds is exactly the kind of thing that, in principle, somebody with enough information and enough control might be able to bias differently. For about 140 years, nobody had the slightest idea how you would begin. Then somebody noticed that the whole problem changes if you are allowed to know things. Part 3. The Demon. At the Door. In 1867, James Clerk Maxwell sat down to write a letter to his friend Peter Guthrie Tait, and in that letter he described a creature that has been bothering physicists ever since. Maxwell was, by any reasonable measure, one of the 2 or 3 greatest physicists who ever lived. He had unified electricity and magnetism and shown that light was an electromagnetic wave, which is the kind of achievement that would ordinarily be enough for one career. He had also done foundational work on the statistical behaviour of gases, which is what he was thinking about when he wrote the letter. The thought experiment he described is this. Imagine a sealed container divided into 2 halves by a wall with a small door in the wall. Both halves are filled with the same gas at the same temperature. Now, temperature is not a property of individual molecules. It is an average. In a gas at any given temperature, some molecules are moving quite fast, some are moving quite slowly, and most are somewhere in the middle. The temperature is the average of all of them, and because the gas on both sides is at the same temperature, the distribution of speeds is the same on both sides. Now imagine a being small enough and quick enough to see individual molecules coming and to operate the door. This being has no tools. It cannot heat anything. It cannot push anything. It cannot add energy to the system in any way. Its only capability is that it can see which molecules are fast and which are slow, and it can open and close a frictionless door at the right moments, so it starts sorting. When a fast molecule approaches the door from the left, it opens the door and lets the molecule through to the right. When a slow molecule approaches from the right, it opens the door and lets it through to the left. Fast molecules going right, slow molecules going left. Everything else, the door stays shut. Let me put you at the door for a moment. You're standing at a shutter no wider than a few atoms, in a space where the air is not a substance but a swarm. Every direction you look, molecules are arriving, some lazy, tumbling along, some coming in fast and hard. You're not doing anything to them. You're not blowing on them, not warming them, not pushing them. Your hand rests on the shutter and your entire job is recognition. That one is fast, open. That one is slow, closed. That one is slow and coming the other way, open. You settle into it, and it becomes almost meditative, and while you work you can feel the two sides of the box slowly separating in character. The right side is getting warmer. The left side is getting colder. The warmth is not coming from you because you have contributed nothing but attention. And after a while you notice, with a small chill that has nothing to do with the left-hand chamber, that in order to do this you have had to keep a running account in your head of what is coming and what you did about it. You have been writing things down. What happens in that box is that one side gets hot and the other gets cold, starting from a state where both were the same temperature. Heat has flowed from a cold place to a hot place. That is precisely what the second law of thermodynamics says cannot happen, and you can now run a conventional engine off the temperature difference you have created, extract work from it, do something useful, and then let the two sides mix back together and start over. Forever. The demon appears to have broken physics using nothing but knowledge. Somebody always pays. That is the instinct every person has when they first hear this, and it is correct, and it took 115 years to work out who. The first thing to understand is that Maxwell was not trying to break the second law. He was trying to make a point about what kind of law it is. His argument was that the second law is statistical rather than absolute, that it holds because of the overwhelming numbers involved, not because of some deep prohibition, and that a being able to work at the level of individual molecules would not be bound by it. He was, in other words, making the same argument Boltzmann would spend the next 30 years formalizing. The demon was a teaching device, but it would not stay a teaching device, because nobody could say precisely where the argument went wrong, and the inability to say precisely where it went wrong is intolerable to physicists. The puzzle sat there for 6 decades. Then, in 1929, a Hungarian physicist named Leo Szilard did something that changed the shape of the problem completely. Szilard was a remarkable figure. He would later be the person who conceived of the nuclear chain reaction, while waiting at a traffic light in London, and who drafted the letter Einstein signed to Roosevelt. And in 1929 he was thinking about Maxwell's demon. Szillard's move was to strip the problem down until it could be calculated. Instead of a box with countless molecules and a complicated sorting operation, he considered a box with exactly one molecule. Here is how it works. You have a cylinder with a single molecule bouncing around inside it. You insert a partition in the middle. The molecule is now on one side or the other. You do not yet know which. You look, and you find out. Say it is on the left. Now, knowing that, you attach a piston to the right-hand side and let the molecule's own pressure push the piston outward, doing work as it goes, until the partition is back where it started and the molecule has the whole cylinder again. You have extracted useful work from a single molecule at a single temperature, drawing the energy out of the surrounding heat bath, and the only thing that made it possible was that you knew which side the molecule was on. Szilard was able to calculate exactly how much work you get from this cycle, and it comes out to a specific quantity involving the temperature and a mathematical constant. What made this historically enormous is that he then argued the acquisition of that one bit of knowledge, left or right, must carry a thermodynamic cost of exactly the same size, or the second law falls. That is the first time in the history of physics that anybody wrote down an equation putting information and entropy in the same units. 1929, 20 years before Claude Shannon founded information theory. Szilard got there first, from the thermodynamic side, chasing a demon. But he got the location of the cost wrong, and so did everyone else for another 50 years. The standard answer through the middle of the 20th century, argued most influentially by Léon Brillouin in 1951, was that the demon has to pay when it looks. To see a molecule, you have to bounce something off it, a photon, say, and that costs energy and generates entropy, and there is your balance. It is a very reasonable answer. It is also wrong, or at least it is not where the unavoidable cost lives. Physicists worked out slowly and with some difficulty that in principle measurement can be done reversibly. You can build a measuring process on paper whose energy cost approaches zero. The looking is not the problem. So the demon was back, and by the 1970s the situation was mildly embarrassing. Here was a puzzle posed in a private letter in 1867, taken seriously by everyone, sharpened into a calculation in 1929, given a plausible answer in 1951, and the plausible answer had just fallen apart. The demon, it turned out, was not being charged for what it learned. It was being charged for what it had to forget. Part 4. The bill nobody wanted to pay. The man who found the answer was not looking for a demon. He was trying to work out the physical limits of computing machines. Rolf Landauer was a German-born physicist who fled the Nazis as a child, ended up in New York and spent most of his career at IBM's research division. In 1961, he published a paper asking a question that nobody had thought to ask seriously. What is the minimum amount of energy a computer must dissipate in order to compute? The intuitive answer at the time was that there is no minimum. Computation is manipulation of abstract symbols, and abstract symbols do not weigh anything. Make your components small enough and efficient enough, and in principle, the energy cost should approach zero. Landauer found that this is almost true, and that the exception is devastating. Almost every operation a computer performs can, in principle, be made reversible, done in a way that consumes arbitrarily little energy, because the information going in can be recovered from the information coming out. Adding two numbers while keeping one of them, copying a bit onto a blank space, flipping a bit, these can all be done for essentially nothing, but erasure cannot. When you erase a bit, when you take a memory element that might have been in either of two states and force it into one known state regardless of where it started, you have destroyed information. Two possible situations have been collapsed into one, and Landauer showed that this operation carries an unavoidable thermodynamic price, paid as heat dumped into the surroundings. The price is small. It is the Boltzmann constant, multiplied by the temperature, multiplied by the natural logarithm of 2. At room temperature, around 300 Kelvin, a normal day indoors, that works out to roughly 3 times 10 to the minus 21 joules for every single bit you erase. Let me put that number somewhere you can feel it. A single photon of ordinary visible light, the sort of thing your eye detects one at a time in a dark room, carries about 4 times 10 to the minus 19 joules. That is more than 100 times the Landauer cost. Erasing a bit of information costs less than 1% of the energy in one particle of light. It is a fantastically small number. It is also, crucially, not zero. And in 1982, a colleague of Landauer's at IBM named Charles Bennett put it together with the demon. Bennett's insight was to ask what happens to the demon over the long run. The demon watches a molecule, decides fast or slow, opens or closes the door. To do that, it has to hold the result somewhere. Even momentarily, even in the simplest possible mechanism, there has to be some physical state that differs depending on what the demon saw. That is a bit of information stored in a physical system. Now run the demon for a while. Molecule after molecule, decision after decision, and the demon's memory fills up. And here is the thing that closes the loop. A demon with a finite memory eventually has to clear it in order to keep working, and clearing it is erasure, and erasure costs, by law, at least the Landauer amount per bit. Do the arithmetic and the numbers line up exactly? The work the demon extracts by sorting molecules is precisely cancelled by the heat it must dissipate to forget what it learned. Not approximately, exactly. The second law of thermodynamics was never in danger. The accounting was just being done on the wrong page. The demon was making a profit on knowledge and paying it all back on forgetting. The arrow is in the ledger, not in the world. I want to stop here for a moment, because there is something in this that I think gets lost when it is presented as a tidy resolution to a Victorian puzzle, and it is the part that has stayed with me since I first read about it. Landauer's principle is not a fact about computers. Computers are just the place he happened to notice it. It is a fact about any physical system that erases a record, and you are a physical system that erases records constantly. Every memory you have lost was, at some point, a physical configuration in your brain. a particular pattern of connection strengths, a particular arrangement of matter that was different from the arrangement that would have been there if things had gone otherwise. And when that memory went, the arrangement did not simply evaporate. It was overwritten. Something physical was pushed into a state that no longer distinguished between what happened and what did not, which means that forgetting warmed the room, not measurably. The amount is so far below anything detectable that it will never be observed and it makes no difference to anything. But it is not zero, and it is not metaphorical. The ordinary human experience of losing things, a name, an afternoon, a face, has an entry in the thermodynamic ledger of the universe. Every one of them is in there, in units of joules, permanently on the side of the books marked heat. I find that oddly beautiful rather than grim, and I have never been entirely sure why. Now, Landauer published in 1961 and Bennett in 1982, and both were making theoretical arguments. The obvious question is whether anybody ever measured it. They did, and it took until 2012. The experiment was led by Antoine Beru and colleagues, and published in Nature. What they built was essentially a single bit made out of a single object. They took a silica bead about a micron across, roughly the size of a bacterium, and suspended it in water inside a laser trap shaped like two adjacent wells. The bead sitting in the left well is a 0. The bead sitting in the right well is a 1. To erase the bit, you manipulate the trap so that the bead ends up in one specific well no matter which one it started in. Then you measure how much energy that costs, which is far harder than it sounds, because the quantity is so small that it is buried under the random thermal jostling of the water molecules. Berut's group had to run the erasure cycle hundreds of times and average the results to pull the signal out of the noise, and when they did, the energy came out at the Landauer bound. Erasing one bit cost what Landauer said in 1961 that it must. That was not the only confirmation. In 2010, Shoichi Toyabe and colleagues in Japan ran the demon in the other direction, building a system that converted information into usable energy, essentially a working Szilard engine at the microscopic scale. Yonakowski and collaborators later did related work with single electron devices, where the bits are individual electrons hopping between metal islands. Different systems, different physics, same answer. Information is physical. That is the sentence Landauer used, and he meant it literally. A bit is not an abstraction floating above the world. It is a configuration of matter, it obeys thermodynamics, and it has a price. I should add one honest caveat because it matters for how you read all of this. Real computers are not remotely near the Landauer bound. A transistor in the device you are listening to this on dissipates something like 1 billion times more energy per switching operation than Landauer's limit requires. The bound has never been a practical constraint on anything and probably never will be. It took a single bead in a laser trap to see it at all, but it is real, and it is the hinge. Because what Landauer and Bennett established between them is that the direction of time in the demon's box is set by an accounting operation, not by the molecules, not by the door, by what gets recorded and what gets erased. And that is a very strange thing to have discovered, because it means the arrow of time in that system is not a property of the gas. It is a property of the relationship between the gas and whatever is keeping track of it. Which was an interesting philosophical curiosity, right up until physicists started looking at systems where the act of keeping track does not sit politely outside the experiment. It sits inside it, and it shoves. Part 5. What looking does to a quantum thing. Everything I have described so far happens in the classical world, and in the classical world there is a convenience so reliable that we build our entire intuition on it without noticing. The convenience is that looking at something barely disturbs it. You put a thermometer in a bath of water and read the temperature. The thermometer does change the water. It absorbs a little heat. It displaces a little volume. But the change is so small relative to the bath that we ignore it entirely, and ignoring it costs us nothing. You photograph a car going past. The photons bouncing off the car and into your lens carry momentum, and they do push on the car, and the amount is so absurdly small that the car's speedometer will never know. You weigh yourself, and the scale does not make you heavier. This is not a law of physics. It is a fact about scale. The probe is tiny compared to the thing probed, so the disturbance is tiny compared to the thing measured, so measurement can be treated as passive. Every measuring instrument ever built for ordinary purposes lives inside that approximation, and the approximation is so good that we forget it is an approximation. Quantum systems destroy it. When you measure a quantum system, and specifically when you measure it in terms of a property that does not sit comfortably alongside its own energy, the measurement does not read a pre-existing value, it changes the system. The outcome you get is random within a distribution that the system's state determines, and once you have that outcome, the system is now in a state consistent with it, which is generally not the state it was in a moment ago. I want to be careful here, because this is the point where explanations usually go wrong. The disturbance is not a technical shortcoming. It is not that our instruments are too clumsy, and a better instrument would be gentler. It is structural. It follows from the mathematical framework itself, and you cannot engineer around it any more than you can engineer around the fact that a triangle's angles add to a straight line. Think of it this way. In the classical world, the system has properties and measurement reports them. In the quantum world, some properties do not have single definite values until something interacts with the system in a way that forces the issue. And forcing the issue is not free. The measurement is not a window, it is a hand. For a long time, this was treated as an all-or-nothing affair. You either measured a quantum system, which meant you hit it hard, got a definite answer, and destroyed whatever delicate arrangement had been there, or you left it alone and learned nothing. Measurement was a guillotine. Then, through the late 1980s and into the 1990s, physicists worked out that you do not have to hit it hard. You can couple your detector to the system very weakly, so weakly that any individual measurement tells you almost nothing and disturbs the system almost not at all, and then do that continuously. Instead of one hard look, you get a continuous gentle gaze. Instead of a single definite answer and a wrecked system, you get a trickle of partial information and a series of small nudges. Do that, and you can watch a single quantum system evolve in real time. The mathematical framework for this is called the quantum trajectory formalism, associated in particular with Howard Carmichael, alongside the quantum feedback framework developed by Howard Wiseman and Gerard Milburn. And what it describes is genuinely new in the history of physics, not the average behavior of many identical systems, which is what quantum mechanics had always given you, but the moment-to-moment history of one. That history looks like a drunkard's walk. The system's state drifts and jitters, pushed one way by its own natural evolution, and another way by the random kicks of the measurement. Watch a single run, and it looks like noise. It has no obvious pattern. It certainly does not look like the smooth, orderly, deterministic evolution that textbook quantum mechanics describes. But run it thousands of times and average the trajectories together, and the smoothness comes back. The average of all those jagged individual histories reproduces exactly the clean equation you would have written down without ever thinking about individual runs. If that relationship sounds familiar, it should. It is precisely the relationship Boltzmann identified between the chaotic motion of individual molecules and the orderly laws of thermodynamics. Randomness underneath, law on top, and the law is the statistics of the randomness. Quantum mechanics arrived at the same architecture from an entirely different direction, roughly a century later, and that means the arrow of time comes back too, in exactly the same way and for exactly the same reason. Here is the fact the whole paper rests on, and it is worth stating slowly. When you continuously measure a quantum system and write down the record, the stream of outcomes, in order, that record is not symmetric. The sequence you actually got is more probable, given the physics, than the same sequence read backward would be. Substantially more probable. Which means that a statistician handed the log, knowing nothing except the rules of the system, could look at it and tell you which end was the beginning. That is the arrow of time in its cleanest possible laboratory form, not a philosophical claim about the nature of becoming, a measurable difference in probability between a sequence and its reverse, and because it is a probability ratio, you can put a number on it. Take the probability of the forward trajectory, divide by the probability of the reverse trajectory, take the logarithm, and you have a quantity that is large and positive when the process is strongly irreversible, and 0 when forward and backward are equally likely, and negative when the reverse is the more probable one. That quantity is not an analogy for entropy production. Averaged over many runs, it is entropy production. The precise mathematical relationship was worked out in the late 1990s, in the Jarzynski equality of 1997 and the Crookes fluctuation theorem of 1999, and those results are the machinery by which the arrow of time stopped being a metaphor and became a number you can calculate for a specific experiment. I want to ground all of this in hardware, because it can start to feel like it is happening on a blackboard. The systems where this is actually done are superconducting circuits, small patterned chips, a few millimeters across, made of aluminium or niobium on silicon, cooled inside a dilution refrigerator to somewhere between 10 and 20 millikelvin. That is 1 to 2/100ths of a degree above absolute zero. For comparison, the coldest thing in the natural universe is the leftover radiation from the Big Bang, sitting at about 2.7 Kelvin. These chips are more than 100 times colder than deep space. They have to be. The energy difference between a superconducting qubit's two states corresponds to a temperature of a few hundred millikelvin, and if the chip were any warmer, ordinary thermal noise would be constantly flipping the thing at random, and there would be no quantum behavior left to watch. Inside that cold, a qubit is coupled to a microwave resonator, and microwave photons leak out of the resonator carrying information about the qubit's state. Those photons go up a chain of amplifiers, the crucial one being a device called a Josephson parametric amplifier, which adds almost no noise of its own, and out to room temperature electronics that record the signal. That signal is the trajectory. That stream of numbers is the log, and it has been routinely recorded in laboratories around the world for well over a decade. Two numbers about that setup matter more than any others, and they will come back later, so I want to plant them now. The first is detector efficiency. This is the fraction of the information leaking out of the system that your apparatus actually catches. Information that escapes into the environment without being recorded is not merely lost to you. It is lost, full stop, and it takes with it any possibility of reasoning about what the measurement did. At perfect efficiency, you know everything the environment knows. In the early days of these experiments, efficiencies were dismal, a few percent, and the trajectories you reconstructed were mostly guesswork. With modern amplification chains, the best setups now exceed 50%, and in some configurations approach or pass 80. That improvement is not a footnote. It is the difference between watching a system and inferring one. The second number is latency, how long it takes between the detector registering something and your equipment being able to act on it. In current circuit setups, that round trip takes tens to hundreds of nanoseconds. Meanwhile, the qubit stays coherent, meaning it stays quantum in the way you need it to for tens to hundreds of microseconds. Divide one by the other, and you get a ratio of roughly 1,000 to 1 in the experimenter's favour. You have time to react, about 1,000 times over, before the thing you're reacting to has stopped existing. And this is not an artifact of one technology. Versions of these measurement and thermodynamics experiments have been run on trapped ions held in electromagnetic cages, on nitrogen vacancy defects in diamond, and on nanoparticles levitated by lasers in vacuum. Different hardware, different energy scales, different laboratories, same behavior. So the situation, by the 2010s, was this. The arrow of time in a quantum system is a statistical property of a measurement record. The record is a physical object, made of microwave photons and voltages and stored bits. And the record is produced by an apparatus that experimenters control completely, which raises a question that, once you have seen it, is very hard to put back down. If the arrow lives in the record and you own the equipment making the record, what stops you from getting there first? Part 6. Where we are before it gets strange. Let me stop and put the pieces on the table together, because we have travelled a fair distance and the shape of the thing only becomes clear when you can see all of it at once. We started with a paper claiming to reshape the arrow of time, and a headline claiming that time had been made to flow backward, and I said I would not close the gap between them until you had what you needed. Here is what you now have. 5 statements, and each one follows from the last. The first is that the fundamental laws do not know which way is forward. Newton, Maxwell, Schrödinger, Einstein. Flip the sign on time and every one of them holds. The reversed film of the shattering cup violates nothing. The second is that the direction we experience is statistical. Boltzmann's answer to Loschmidt was that disorder increases not because a law commands it, but because disordered arrangements outnumber ordered ones by a margin with no comparison in ordinary experience. The arrow is a bias in the odds. The third is that records are what make the statistics bite. Maxwell's demon appears to beat the odds precisely because it knows things, and Szilard showed that knowing can be converted directly into work. Information is not a description sitting alongside the physics. It is part of the physics. The fourth is that records cost heat. Landauer in 1961 showed that erasing 1 bit dissipates energy by law, and Bennett in 1982 showed that this is exactly where the demon's apparent profit goes. Beru measured it in 2012 with a single bead in a laser trap. The books balance, and they balance on the erasure line. And the fifth, which is where the last part left us, is that in a quantum system, the record is not written by a passive observer standing outside the experiment. It is written by an apparatus that reaches in and shoves. The arrow of time in a monitored quantum system is a property of the measurement log, and the measurement log is produced by equipment that human beings design, own, and operate. Put those five together and you get a sentence that would have sounded absurd to any physicist before about 1980, and sounds merely provocative now. Whoever controls the record controls the direction. I want to be precise about what has and has not been claimed here, because this is the point in a story like this where things usually get away from people. Nobody has said the past can be changed. Nobody has said information can travel backward. Nobody has said that any of this applies to objects you can see, or to your life, or to anything that has ever happened to a person. Every single result I have described takes place in a system of 1 or 2 degrees of freedom, held near absolute zero, watched by equipment that costs more than a house. What has been established is narrower and I think stranger. It is that the direction of time in these systems is not a fact about the system. It is a fact about the relationship between the system and whatever is keeping track of it. Change the bookkeeping and you change the direction, because the direction was never anywhere else. There is a useful way to hold the distinction. Think about a ship's log. The log is not the voyage. If somebody rewrites the log so that the entries read convincingly in either order, the ship still went where it went, the storm still happened when they happened, and nobody aboard has travelled anywhere new. What has changed is what the log can tell you, and ordinarily that would be an uninteresting kind of forgery, except that in this case, physics has spent 150 years failing to find the arrow of time anywhere except in the log. If the direction was only ever a feature of the record, then editing the record is not falsifying the evidence. It is the whole phenomenon. That is the door. And for decades, everyone could see the door and nobody could reach the handle, because there was one thing missing from the chain. You would need to be able to reach into the record while it is being written, not analyze it afterward, not predict it beforehand. Reach in real time, while the ink is still wet, and push back against the very thing that is writing it. That sounds like a demand for magic. It is not. It is a demand for engineering, for a detector fast enough, a control system quick enough, and a system that stays quantum long enough for the loop to close. 3 specifications, all of them boring, all of them expensive, none of them impossible. And in 2019, in a basement laboratory in Connecticut, a group of physicists did exactly that to a single quantum event. They did not set out to touch the arrow of time. They set out to catch something that a century of textbooks said could not be caught. Part 7. The jump they caught mid-flight. The thing they caught is called a quantum jump, and it has one of the strangest histories in physics. Niels Bohr introduced the idea in 1913. His model of the atom had electrons occupying specific allowed orbits, and to move between them an electron did not travel through the space in between. It simply stopped being in one orbit and started being in the other. The transition was instantaneous, discontinuous, and had no intermediate stages, because there were no intermediate stages available to have. Erwin Schrödinger hated this with an intensity that survives in the historical record. He had built quantum mechanics on a continuous wave equation precisely to get away from jumping, and he never accepted that jumps were real physical events rather than artifacts of a bad model. In 1952, he wrote a paper called "Are There Quantum Jumps?" The answer he wanted was no, and he is on record in conversation with Bohr saying that if all this damned quantum jumping were going to stay, then he was sorry he had ever gotten involved with quantum theory in the first place. Bohr won that argument. In 1986, 3 independent research groups working with single trapped ions observed quantum jumps directly for the first time. You hold one ion in an electromagnetic cage, you shine light on it, and it fluoresces steadily. And then, abruptly, it goes dark, because it has jumped into a state that does not fluoresce. It stays dark for a while. Then, just as abruptly, the light comes back. Watching it happen is watching a single atom switch off and on at random. It is worth pausing on how odd that observation was for the people who first made it. For 60 years, quantum mechanics had been a theory about ensembles, about what happens on average when you do the same thing to a great many identical systems. The equations gave you probabilities, and probabilities are statements about populations. Nobody had ever watched one. And then, suddenly, 3 groups in the same year were sitting in front of screens watching a single atom make individual decisions in real time, and the decisions were arriving one at a time, and there was no average to hide behind. Some of the physicists involved described it as the first time quantum mechanics had felt less like mathematics and more like biology. So by the 1990s, the settled picture was this: quantum jumps are real, they are abrupt, they occur at random times that nothing can predict, and once one has happened, it has happened. There is no catching it partway through, because there is no partway through. That picture lasted until 2019, when a group at Yale led by Zlatko Minev, working with Michel Devoret and colleagues, published a paper in Nature with a title that reads almost like a challenge: to catch and reverse a quantum jump mid-flight. The trick they used was indirect, and it is elegant enough to be worth understanding. They built a superconducting artificial atom with 3 accessible energy levels rather than 2. Call them the ground state, the state they cared about, and a third auxiliary state. The jump they wanted to catch was between the ground state and the state they cared about. And here is the key point: that jump is invisible while it is happening, because looking at it directly would destroy the very thing they wanted to observe. So they did not look at it. They looked at the auxiliary state instead. The auxiliary state was coupled to the ground state, and was driven so that, as long as the system was sitting in the ground state, it fluoresced continuously, a steady stream of microwave photons pouring out into the detector. That fluorescence was not information about the jump. It was information about the system still being in the place the jump would depart from, which meant that when the fluorescence stopped, something had changed. Let me put you in that room. It is a laboratory in New Haven, and most of what matters is happening inside a metal cylinder about the height of a person, hanging from the ceiling, wrapped in layers of shielding. Inside it, stage by stage, the temperature drops. 4 Kelvin, then 1, then 100 millikelvin, then 10. At the bottom, on a chip a few millimeters across, sits the artificial atom. Nothing about the room looks dramatic. There is a rack of electronics, a screen, the low continuous hum of pumps. On the screen there is a signal, and the signal is noise, a rough jittering trace, the fluorescence coming off the auxiliary transition. It jitters and jitters and jitters. Then, for an interval too short to notice if you were not watching for it, it goes quiet, not silent, just quieter than it should be, for longer than chance allows. That silence is the beginning of a jump. The electronics recognize it in real time, faster than anything human, and fire a precisely shaped pulse back at the chip. And the jump, the thing physics had spent a century describing as instantaneous, uncatchable and random, stops. It does not complete. The system returns to where it started, and the fluorescence comes back, and on the screen the trace resumes its ordinary jittering as if nothing had been about to happen. They did it again, and again. And the reversal worked reliably enough that the word they used in the paper was deterministic. What that experiment established is worth stating carefully, because it is bigger than it looks. First, the jump is not instantaneous, it has duration. Once it begins, it proceeds continuously and coherently through intermediate configurations, and it is only the endpoints that look discontinuous. Schrödinger, in a sense, was partly right after all, and he had been dead for 58 years. Second, and more important for where we're going, the randomness is only randomness until you are watching closely enough. The moment a jump starts is genuinely unpredictable. But once it has started, its course is not. Given a warning and enough speed, you can intervene in it. Third, and this is the part that matters most, monitoring plus fast feedback equals control over an event that was assumed to be irreversible. That is the entire capability. Watch closely, understand what the watching is telling you, act inside the window, and something that was supposed to only go one way can be sent back. The word coherent is doing quiet work in that description, and it is worth unpacking because it is the difference between a nice trick and a fundamental result. If the jump was simply a fast but ordinary transition, a system tumbling from one state to another through some messy sequence, then catching it would be a matter of reflexes, like grabbing a falling glass. It is not that. Coherent means the system, during the jump, is in a definite and predictable quantum relationship between the two states, evolving smoothly and lawfully. That is why the reversal works reliably rather than occasionally. They were not grabbing at something falling. They were reading a trajectory they could calculate and applying the precise operation that runs it backward. There is a practical consequence that made this result matter to people who care nothing for the philosophy of time. The single largest obstacle to building useful quantum computers is that qubits decay. They leak their information into the environment through exactly these kinds of random transitions, and every quantum error correction scheme in existence is a strategy for detecting and repairing that damage after it happens. Yale demonstrated something categorically different, catching the damage while it is occurring and preventing it from completing. Whether that ever becomes practical at scale is an open question, but it reframed error correction from a cleanup problem into an interception problem, and that is the kind of reframing that funding agencies notice. The numbers that made it possible are the ones I planted earlier. The feedback loop closed in a matter of nanoseconds. The system stayed coherent for microseconds. The detection chain, built around Josephson parametric amplifiers, captured enough of the escaping information that the silence in the signal was distinguishable from ordinary noise. Take away any one of those three and the experiment does not work. Now, I want to be clear about the limits of what Yale did, because it is not the same thing as what the 2026 paper proposes. Yale reversed one event, a single jump caught in progress, sent back where it came from. That is remarkable, and it is local, and it is finite. It says nothing directly about the arrow of time. The paper we started with asks a much larger question. Not, can you reverse one thing that is happening, but can you take the entire statistical character of the record, the property that lets an outsider tell which end came first, and turn it around? Those are different in the way that stopping one car is different from reversing the direction of traffic. But Yale proved the mechanism exists. It proved that a monitored quantum system with a fast enough loop around it is not a thing that happens to you. It is a thing you can steer, which leaves exactly one question, and it is a question about how you build the steering wheel. Part 8. The Hamiltonian that imitates a measurement. To understand what Garcia Pintos, Liu and Gorshkov actually built, you need one piece of vocabulary, and I am going to give it to you without a single equation. The word is Hamiltonian. A Hamiltonian is the object in physics that describes how a system's energy depends on its configuration. That is all it is. If you tell me where everything is and how fast it is moving, the Hamiltonian tells me how much energy that situation contains. It is named after William Rowan Hamilton, an Irish mathematician working in the 1830s, and it is one of those inventions that turned out to be far more important than its inventor could have known. The reason it matters is this: once you have the Hamiltonian, you have the future. In both classical and quantum mechanics, the Hamiltonian generates the evolution. It tells the system how to move. Give a physicist the Hamiltonian of a system, and they can, in principle, tell you everything that system will ever do. So a Hamiltonian is not just a description of energy. It is a recipe for change, and crucially, it is a recipe for smooth, continuous, lawful, reversible change. Evolution under a Hamiltonian is the well-behaved kind of physics, the kind that runs equally well in either direction, the kind that conserves information, the kind that Loschmidt's objection applies to. Now hold that thought, because here is the other half. Measurement in the standard story is the thing that is not Hamiltonian evolution. This is the great structural oddity at the heart of quantum mechanics, and it has been there since the 1920s. The theory has two rules. Rule 1 says that when nobody is measuring, systems evolve smoothly, continuously, reversibly, according to the Hamiltonian. Rule 2 says that when a measurement occurs, the system jumps abruptly to a state consistent with the outcome. The change is not smooth, it is not reversible, and it is not generated by any Hamiltonian. Two rules, printed on facing pages, and no law in the book saying when to switch from one to the other. That is the measurement problem, and it is the oldest unresolved question in the field. So when I tell you that the central move of this paper is to construct a Hamiltonian that reproduces the effect of a measurement, you should feel a small jolt. Those are supposed to be the two things that cannot be each other. Here is how the trick works, and it hinges on a subtlety that took decades to see clearly. The reason measurement seems un-Hamiltonian is that it is random. You cannot write a smooth deterministic recipe for something whose outcome is unpredictable. But the randomness is only in which outcome you get. Once you have the outcome, once the detector has clicked and you're holding the result in your hand, the update to the system's state is completely determined. There is nothing random left. Given the outcome, the change is a specific calculable transformation, and a specific calculable transformation of a quantum state is exactly the kind of thing a Hamiltonian can generate. There is a nice way to see why this is not cheating. Imagine a card dealt face down from a shuffled deck. Before you look, the situation is genuinely uncertain, and no deterministic account of it is possible. After you look, and the card is the 7 of clubs, everything that follows from it being the 7 of clubs is perfectly determined. The uncertainty was never in the physics of what a 7 of clubs does. It was in which card you got. Separate those two things, and the determinism was there all along, waiting underneath the randomness. The construction in this paper is the quantum version of that separation, applied continuously, thousands of times a second, to a system that is being dealt a new card at every instant. This also tells you immediately what the scheme's weak point must be. It depends entirely on knowing the outcome. If your detector misses part of what the system emitted, if some of the information leaks into the environment without ever reaching your electronics, then you do not know which card was dealt, and the transformation you compute will be the wrong one. This is why detector efficiency, that number I planted 2 parts ago, is not a quality of life improvement. It is the load-bearing specification of the entire proposal. So the construction goes like this. You're watching a system continuously. At every instant the detector gives you a reading. That reading tells you, with certainty, what kick the measurement just gave the system. And because you know the kick, you can compute a control field, a specific pattern of microwave pulses, a specific arrangement of energies, whose effect on the system over the next tiny interval is identical to the kick the measurement just delivered. You have built a knob that does what looking does. Sit with that for a second, because it is genuinely strange. The measurement disturbance was supposed to be a special, irreducible, non-mechanical intrusion into the quantum world, and it turns out that, conditioned on the outcome, it can be perfectly imitated by an ordinary energy field of the sort you already use to run quantum logic gates. Nothing exotic. The same hardware, the same amplifiers, the same waveform generators, the same pulses you would use to flip a qubit in a computation. Now, why would you want a knob that imitates a measurement? You already have measurements. Why build a machine to do what the machine you already have is doing anyway? Because a knob can be turned the other way. That is the whole idea. A measurement gives you a kick you did not choose, in a direction you find out about only after it happens. But if you can synthesize that same kick with a control field, then you can also synthesize its opposite. You can build the field that does the reverse of what the measurement just did, and apply it immediately. This is a feedback loop, and it is worth describing as the piece of engineering it actually is, because feedback loop sounds abstract and it is not. It is a physical circuit with a latency budget. The detector registers a reading. That reading travels up the amplifier chain, out of the refrigerator into room temperature electronics. Those electronics do a computation, small, but a real computation, to work out what control pulse is required. The pulse is synthesized and sent back down into the cold and lands on the chip. And all of that has to happen fast enough that the system has not moved on. Every part of that loop is something engineers already build. The thermostat in your house is a feedback loop. The cruise control in a car is a feedback loop. Aircraft have been flown by feedback loops since the 1940s. What is new here is not the concept. It is the timescale, and the fact that the thing being corrected is the disturbance created by the act of observation itself. It is worth being concrete about what a control field physically is, because the phrase sounds like something from a spacecraft. On a superconducting chip, it is a shaped burst of microwave radiation delivered down a coaxial line, a waveform specified as a sequence of amplitudes and phases lasting some tens of nanoseconds. The art of designing those waveforms is a mature engineering discipline with its own optimization algorithms, developed originally for nuclear magnetic resonance and inherited wholesale by the quantum computing world. When physicists say they constructed a Hamiltonian, what an engineer hears is, they specified a pulse. The gap between the abstraction and the hardware is smaller here than in almost any other part of fundamental physics, and that is precisely why this paper can propose an experiment rather than a thought experiment. Now I want to head off a misunderstanding, because it is the one everybody has at this point. This is not undoing the measurement. You cannot undo a measurement. The information has left the system. It is in the amplifier chain, in the recorded data, in the state of the room. Getting it back is precisely as impossible as unringing a bell, and for the same thermodynamic reasons we spent 2 parts establishing. Nothing in this paper claims otherwise. What the scheme does is different and more subtle. It does not remove the information. It counteracts the disturbance while keeping the information. You still know the outcome. You still have the record. What you have changed is the physical consequence that the outcome had for the system. Think of it this way. Somebody shoves you in a crowd. You cannot make the shove not have happened, and you cannot unknow that you were shoved. But if you are quick, you can step in a way that leaves you exactly where you would have been if nobody had touched you. The shove is in the record. Its effect on your position is not. That is the operation, repeated continuously, thousands of times over the life of a single experimental run. There is a second use for the same construction, and the authors mention it almost in passing, though I suspect it will turn out to matter more than the headline application. If you have a Hamiltonian that reproduces what monitoring does to a system, then you also have a Hamiltonian that reproduces what monitoring did to it, which means you can run the evolution of an open quantum system backward as a simulation. Not backward in time in any physical sense, backward as a calculation, the way an accountant reconstructs a balance from a series of transactions. That is genuinely valuable, because a huge class of problems in chemistry, materials science and error diagnosis consists of staring at the state a system ended up in and trying to work out how it got there. Open quantum systems are notoriously hard to run in reverse, because information has leaked out, and reversing requires putting it back. A construction that handles the bookkeeping is a real tool, and there is one more requirement that decides whether the whole thing lives or dies, which is that all of this must happen inside the coherence window. Once the qubit has decohered, once its quantum character has bled out into the environment, there is nothing left to steer, so the loop must close in nanoseconds while the system survives for microseconds, which, as I mentioned earlier, gives about 1,000 to 1 in the experimenter's favour. That ratio is the entire reason this is a proposal about superconducting circuits, rather than a proposal about atoms or molecules or anything you could hold. It is not that other systems are uninteresting. It is that other systems are too slow to catch, or too fast to see, or leak too much of their information into places nobody is listening. So, a Hamiltonian that imitates a measurement, driven by a feedback loop that acts inside the coherence window, using hardware that already exists. That is the machine. The question is what you do with it once you have it, and the answer is that this particular knob has 3 settings, and the third one is the one that made the headlines. Part 9. Cancel, Amplify, Overcorrect. 3 settings. Let me name them before I explain them, because the shape of the thing is easier to hold if you know where it is going. The first setting is Amplify, the second is Cancel, the third is Overcorrect, and the third one is where every headline about this paper came from. Start with Amplify, because it is the least surprising and it establishes that the knob is real. Recall what the measurement is doing. Every instant it delivers a small random kick to the system, and every one of those kicks contributes to the asymmetry in the record, the property that lets a statistician tell forward from backward. The more kicks, and the harder they are, the more strongly directional the record becomes. Entropy production goes up. The arrow sharpens. So if you set your control field to reproduce the measurement kick and add it on top of the real one, you get a system being disturbed twice as hard as it is actually being watched. The record becomes more irreversible than the physics alone would make it. You have manufactured an arrow of time steeper than the one nature was supplying. That is not philosophically interesting, but it is an important demonstration, and in experimental physics this kind of check is often the first thing anybody does. Before you claim a control system can turn a quantity down, you show it can turn the quantity up, because turning it up is the easy direction, and any failure shows itself immediately. It proves the knob is connected. It shows the control field is genuinely acting on the same quantity that measurement acts on, in the same units, in the same direction. If Amplify did not work, nothing else would. Now turn the knob the other way. The second setting is Cancel, and this is where it starts to matter. Instead of adding the imitation kick to the real one, you subtract it. The measurement pushes. The control field pushes back with exactly equal force. The two disturbances meet and cancel, and the system carries on as though nobody were watching it, except that somebody is watching it, and you have the entire record in front of you. What happens to the asymmetry? It drains away. Remember how we quantify this. The arrow is the logarithm of the ratio between the probability of the forward trajectory and the probability of its reverse. When that number is large and positive, the process is strongly irreversible and the direction is obvious. When it is 0, the forward and backward readings of the record are equally likely, and there is no fact of the matter about which end came first, At the cancel setting, that number goes to 0. I want to be very careful about what that means, because it is easy to inflate. It does not mean time stopped. It does not mean the experiment froze. The system is evolving, the detector is recording, the clock on the wall is ticking exactly as it always was. What it means is that the specific statistical footprint by which irreversibility announces itself has been erased from the log. Hand that record to somebody who knows the physics and does not know which way you played it, and they cannot tell you. Both readings are equally consistent with everything they know. That by itself is a meaningful result. Making a physical process statistically time-symmetric is not something anyone had previously been able to do on demand. But the authors do not stop there. The third setting is overcorrect and the whole paper turns on it. Instead of pushing back with exactly equal force, you push back harder, you overshoot. The control field does not merely undo the measurement's disturbance. It goes past undoing it and drives the system in the opposite direction, and the number that measures the arrow does not stop at 0. It goes negative. A negative value means that the reverse of the trajectory you recorded is now more probable than the trajectory you recorded. Read the log backward and it makes more sense, is a better fit to the physics, is what you would have predicted, than reading it forward. Let me put you at the console. There is a screen in front of you with two things on it. On the left is a live trace of the measurement record, scrolling by, the raw stream of outcomes. On the right is a single number, updating a few times a second, and that number is the asymmetry. Beneath your hand is one dial. At the current setting, the number reads strongly positive, and the trace on the left has an obvious character to it. You do not need training to see it. There is a texture, a directionality, the way you can tell without being told that a video of a diver is playing forward. Whatever is happening on that screen is clearly going somewhere. You begin to turn the dial. The number starts to fall. Slowly at first, then steadily. And as it falls, the trace changes. The texture flattens. Whatever it was that made the record look like it was heading in a direction begins to smooth out. Not because the signal is getting weaker, but because it is losing its grain. The number passes through 1, and then a fraction, and then it is sitting at 0, jittering slightly around it, and the trace on the left has become something you could play in either direction and never know. You keep turning, and the number goes below 0, and keeps going, and the texture comes back, but wrong, backward. The same kind of directionality that was there at the start, pointing the other way. If you had walked into the room at this moment and been handed the record, you would have said, without hesitation, that somebody was playing it in reverse. Nobody is. It is being recorded live, right now, forward, at the ordinary rate. That is the result. I want to draw out why the third setting is a much stronger claim than the second, because this is the part that separates a clever demonstration from a genuine finding. Cancelling an effect is ordinary engineering. It is what noise-cancelling headphones do. You measure a disturbance, generate its opposite, add them together, get silence. Nobody's astonished by it, and the fact that you can cancel a thing tells you mostly that you understood it well enough to model it. Overshooting deliberately is different, and it is different in a specific way. If the arrow of time were a binary property, either a process is irreversible or it is not, then cancellation would be the end of the road. You would flatten it to 0, and there would be nowhere else to go. And pushing harder would just produce nonsense, an artifact, a number with no meaning attached. But it is not nonsense. Push past cancellation, and you get a well-defined negative asymmetry that corresponds to a real, physically interpretable situation. A system whose recorded history is a better fit to backward evolution than forward. Which tells you something about the underlying quantity. The arrow of time in these systems is not a switch with two positions. It is a continuous parameter. It can be stretched, sharpened, blurred, flattened, or inverted, and every value in between is available and means something. That is a genuinely new thing to know about a property that most people, including most physicists, have spent their lives treating as a background condition of existence rather than as a dial. I also want to sit for a moment with the settings in between, because they are easy to skip past and they are quietly the most unsettling part. Between amplify and cancel, there is a whole continuum, and the authors describe the arrows produced there as stretched and blurred. A stretched arrow is one where the directionality is still present but weakened. The record still tells you which way it went, but it tells you less confidently, over a longer stretch of data, with less certainty per unit of time. A blurred arrow is one where the signal is there but smeared, so that at short timescales the record looks symmetric, and only over long stretches does a preference emerge. Think about what that means. We're used to the direction of time being a fact, a yes or no property of a process. What this describes is a direction of time with a strength. A process can be a little bit irreversible. It can be irreversible at one timescale and reversible at another. It can be mostly directionless with a faint bias. None of that is available in the intuitive picture, where time either flows or it does not. And there is something almost vertiginous about noticing that this was always true, and nobody bothered to say it. The asymmetry we call the arrow of time has always been a quantity rather than a fact. In ordinary life it is simply so enormous. The ratio between forward and backward probability for a shattering cup is a number with more digits than there are particles in the room, that the distinction between very large and infinite never came up. We rounded a number to a certainty, and then built our entire intuition about existence on the rounding. What this experiment does is find a system where the number is small enough to move and then move it. There is a satisfying historical symmetry in this too, which I do not think is a coincidence. Loschmidt's objection, back in 1876, was a thought experiment. Reverse the velocity of every molecule and the gas will unmix. It was posed as an impossibility, an argument about what could not be done in order to make a point about what the second law really is. Nobody imagined actually doing it. You would need to know the position and velocity of every particle, and to reverse each one individually, which for any real gas is permanently out of reach. What this construction does is Loschmidt's objection carried out. Not on a gas, on a system small enough that you genuinely can track everything relevant about it, using a detector fast enough to keep up, and a control field precise enough to act. The thought experiment posed to prove a point has become a procedure with a parts list. So that is the machine and that is what it does. A knob with 3 settings that acts on the direction of time in a monitored quantum system, built out of pulses that existing hardware can already produce. Which brings us finally to the question you've been holding since the first sentence of this video. They turned the dial past 0. The number went negative. The record now reads better backward than forward. Does that mean time ran backward? Part 10. What reversed? Actually means. No, I want to give you that answer flatly and immediately, because you have been carrying the question for a long time, and it would be a cheap trick to keep you waiting for it any longer. Nothing travelled backward. No object, no signal, no piece of information reached its own past. No moment was revisited. Nobody in that laboratory experienced anything other than 1 second following another in the ordinary way, and the equipment recorded events in the order they occurred, and if you had been standing in the room you would have noticed nothing at all. So what was reversed? The statistical signature, nothing else. The property by which an outside observer handed the record and told nothing about how it was produced could work out which end was the beginning. That is a real, well-defined, physically meaningful property, and turning it around is a real achievement. It is also, unmistakably, a property of the record and not a property of the world the record describes. The film analogy is the one that clarifies this best, so let me do it properly because it is usually done badly. Suppose you film a pendulum swinging in a vacuum. The footage looks identical played in either direction because the motion is time-symmetric. A pendulum swinging left to right looks exactly like a pendulum swinging right to left. Now suppose someone hands you that footage and asks which way it was shot. You cannot tell. The information is not in the film. Has time reversed for the pendulum? Obviously not. The pendulum swung when it swung, in the order it swung, and the fact that your recording of it cannot distinguish forward from backward is a fact about your recording. Now, everything the 2026 paper does is a much more sophisticated version of that. Instead of finding a system that happens to be symmetric, they take a system that is emphatically not symmetric and manipulate it until its record loses and then reverses the asymmetry. That is a far harder thing to do, and it required genuinely new mathematics. But the category of the result is the same. What has been altered is what the record can tell you. The arrow is in the ledger, not in the world. I introduced that line a long way back when we were talking about Landauer and Bennett and the demon's missing prophet, and at that point it was doing modest work. It was an accounting resolution to a Victorian puzzle. The book's balance if you look on the right page. Here it is doing everything. It is simultaneously the reason the headline is wrong and the reason the result is remarkable, and those two things are the same fact wearing different clothes. And I want to slow down here, because there is something underneath this that I do not think should be skipped past as a technicality. When a person hears that scientists have reversed time, something moves in them that is not intellectual curiosity. It is not really a question about physics. Some part of the mind, below the part that reads headlines, hears that sentence and thinks about a room that no longer has someone in it, about the last ordinary Tuesday before a diagnosis, about a conversation that went badly and cannot be had again. Nobody consciously believes a paper in a physics journal is going to give any of that back. But the hope is not conscious, and it does not need to believe anything to be present. The honest answer is that nothing came back. The cup is still broken. Everything that happened, happened, and stays happened, and no amount of control over any quantum system alters that by the smallest measurable amount. The paper does not offer this, and its authors have never suggested otherwise. Whatever you have lost, and the machinery I have spent an hour describing is entirely silent on the subject. And the reason it is silent is, I think, the most interesting thing in the whole story. It is not that the reversal is fake, or that it failed, or that the physicists overreached. The reversal is real. It works. It is that the arrow of time was never in the world in the first place. It was in the record. And that means reversing it in the record is not a partial success or a technicality. It is the complete thing, done properly, all the way. There is nothing else there to reverse. Which is a strange kind of consolation and a strange kind of desolation at once, and I do not think you have to resolve it into one or the other. Both halves are true. The arrow of time is a fact about bookkeeping, and the past is still gone. If all of this feels familiar, there is a reason, and it is worth a short detour because it teaches you how to read the next one of these announcements when it arrives. In March of 2019, a group led by Gordy Lesovic, working with colleagues in Russia, the United States and Switzerland, published a paper in Scientific Reports called Arrow of Time and its reversal on the IBM quantum computer. The coverage that followed was almost word for word the coverage this paper got. Physicists reverse time, scientists turn back the clock, Russian researchers send a quantum computer into its own past. What Lesovic's group actually did was elegant and much narrower. They noted that a quantum state which has spread out and become complicated could, in principle, gather itself back into its original simple form, the quantum version of Loschmidt's unmixing gas, and that the odds of this happening spontaneously are so small as to be irrelevant. So they wrote an algorithm. They ran a state forward on an IBM quantum processor until it had scrambled, then applied a designed sequence of operations that returned it to where it started. The evolution was undone. That is a real and useful result about quantum algorithms. It is not time travel, and it was not claimed to be. The state went back. The clock did not. The computer that ran the operation is a second older than when it began. The electricity bill went up, and every event in the laboratory happened in the order it happened. 2 different results, 7 years apart, using different mechanisms, both about the reversibility of quantum evolution, both accurately and carefully described by their authors, and both delivered to the public inside the same wrapper. That pattern is not going to stop, and the tell is always the same. Look for what the authors said, not what the headline said, and pay particular attention to the qualifiers, because the qualifiers are where all the meaning lives. There is one honest complication I should add, because I have been saying the fundamental laws are time-symmetric, and that is very slightly untrue. They are almost time-symmetric. In 2012, the Babar collaboration at the Stanford Linear Accelerator Center reported the direct observation of time reversal violation in the behavior of certain unstable particles called neutral B mesons, a genuine measured asymmetry between a process and its reverse, built into the laws themselves rather than emerging from statistics. Related asymmetries turn up in neutrino experiments, including results from the T2K collaboration in Japan, so the laws are not perfectly indifferent to direction. There is a preference in there, in one corner of particle physics, and it is real, but it is tiny, and it lives in the wrong place. The asymmetry is roughly a part in 1,000 in exotic particles that barely exist for long enough to be measured. The thermodynamic arrow, the one that shatters cups and cools coffee, is overwhelming, involves no exotic particles, and shows no sign of caring what B mesons do. A minority of serious physicists think the connection between the two will eventually turn out to matter. Most think they are simply unrelated. Nobody has shown either way. Let me clear away a few things that people reliably attach to results like this, because clearing them away leaves more room for what is actually here. Nothing in this violates causality. The no-signaling theorems of quantum mechanics, the results guaranteeing that entanglement and measurement cannot be used to send information faster than light or backward in time, are untouched. They are not interpretation dependent and they are not fragile. This paper does not go near them. Nothing in this favours any particular interpretation of quantum mechanics. If you are a many-worlds person, nothing here helps or hurts you. Same if you prefer pilot waves, or spontaneous collapse, or the various epistemic readings. The construction operates at the level of measurement records and control fields, which every interpretation agrees about. Anyone telling you this result proves their favourite picture of quantum mechanics is selling something, and nothing in this is a step toward doing it to anything bigger. That last one deserves a moment, because it is the one where the honest answer is more subtle than a flat no. There is no law forbidding it. That is the uncomfortable part. Nothing in physics says the arrow of time may be reshaped in a system of 1 degree of freedom, but must remain fixed in a system of 1 trillion. The barrier is not legal, it is practical, and the practical barrier is so enormous that it functions as an absolute one. Here is the scale of it. To do this, you must monitor every relevant degree of freedom of the system, and push back against each disturbance in real time. In a superconducting qubit, that is a small number of things to track. In a single gram of ordinary matter, there are something like 10 to the 23rd particles, each with several degrees of freedom, all interacting. You would need a detector capturing essentially all the information leaking out of every one of them, and a control system computing and applying a correction to every one of them, inside a coherence window that for warm, large objects is not microseconds, but something closer to 1/1000 of a second. That is not a hard engineering problem. It is a problem whose difficulty grows so violently with size that the universe does not contain enough matter to build the apparatus. So the honest statement is, forbidden in principle, no. Hopeless in practice, comprehensively and permanently yes. And those two things are both true, and people who want this to be spooky quote only the first, and people who want it to be boring quote only the second. What is left, when you have stripped away the time travel and the causality violation and the scaling fantasy, is this. A group of physicists worked out how to take the most fundamental seeming asymmetry in nature, locate exactly where it lives, and turn it around. And where it lives turned out to be the accounts. That would be enough for one paper. But it is not actually the part with the largest consequences, and the part with the largest consequences got almost no coverage at all, because it does not sound like science fiction. It sounds like an engine. Part 11. The engine that runs on being watched. Every engine you have ever encountered works the same way, and it has done since Sadie Carnot worked out why in 1824. You need something hot and something cold. Energy flows from the hot thing to the cold thing, because that is what energy does, and on the way past you put something in its path that the flow can push. A piston, a turbine blade, a thermocouple. The work you extract comes out of that flow, and the amount you can extract is set entirely by how big the temperature difference is. That is the steam engine. It is also the internal combustion engine, the jet engine, the coal plant, the nuclear plant, and the refrigerator running backward in your kitchen. Every one of them has a hot side and a cold side, and if you take away either one, the machine stops. Carnot's result is that this is not an engineering limitation. It is a constraint on what an engine can be. The engine described in this paper has neither. There is no boiler, there is no radiator, there is no temperature difference anywhere in the apparatus that the engine is drawing on. The entire device sits at, essentially, one temperature, a few thousandths of a degree above absolute zero, and it produces work anyway. The fuel is the measurement. Let me put you inside the cycle, because this is the point where it stops being an abstraction. You're looking at a single quantum system, one qubit, one two-state object, the smallest thing that can be said to have a state at all. It is being continuously monitored. Photons are leaking out of it, carrying information, arriving at a detector. And here is the thing that is easy to forget, that monitoring is not free for the system either. When a measurement disturbs a quantum system, the disturbance is not just informational, it is energetic. The system's energy changes. Measuring in a way that does not sit comfortably alongside the system's own energy structure means that, on average, energy gets pushed in. The act of looking deposits energy in the thing being looked at. Ordinarily, that energy is a nuisance. It is heating, It is noise. It is the reason measurement is destructive. But now you have a feedback loop. At every instant what the measurement just did, so you can steer. You can arrange the control field so that the system is always in a configuration from which the deposited energy can be drawn back out as useful work rather than dumped as disorder. Monitoring pushes energy in. Feedback shapes the system so the energy comes out somewhere you can catch it. Then it happens again, and again. Continuously, thousands of times for as long as you keep watching. Go looking for the hot side of that machine and you will not find one. Walk around it. Here is the chip, a few millimeters of patterned metal on silicon, and it is cold. Here is the mounting stage it sits on, and that is the same cold. Here is the shielding and the coaxial line carrying signals away, and the point where the line leaves the coldest stage, all of it at the same temperature, within the precision of any thermometer that works down there. You put your hand out metaphorically, looking for the warm spot every engine you have ever met has had somewhere on it, and there is no warm spot. There is nothing burning. There is no flame, no reservoir, no gradient, no direction for heat to flow because there is nowhere for it to flow to, and work is coming out. Follow it backward to find the source, and the trail leads somewhere you were not expecting. It does not lead to a fuel line. It leads to the detector, to the fact that something, somewhere, is registering what this system is doing. Interrupt that. Stop the monitoring. Let the qubit sit unobserved, and the engine stops. Not because you cut the power, because you stopped paying attention. The fuel is the looking. Somebody always pays. I said that a long way back, standing at the demon's door, and it was a suspicion then, and by the time we got to Landauer it had become a law. And here is a machine that appears, quite flagrantly, to break it. It does not, of course. But where the payment goes is worth being precise about, because the resolution is exactly the resolution Bennett gave in 1982, arriving from a new direction. Draw a boundary around the qubit, and the answer is that the engine produces work from measurement, full stop. Widen the boundary, and the picture changes entirely. That detector is a chain of amplifiers. Those amplifiers sit inside a dilution refrigerator, and a dilution refrigerator is a machine the size of a small car that consumes several kilowatts continuously to hold a fingernail-sized chip at 10 millikelvin. The control electronics are a rack of room temperature equipment drawing more. The computer working out the feedback pulses draws more still. The engine returns energy measured in units where a single photon is a large quantity. The apparatus running it consumes enough power to heat a house, so nobody's getting anything for free, and no responsible person in this field has ever suggested otherwise. The Los Alamos announcement itself went out of its way to note that the second law is not violated once all the thermodynamic costs are accounted for. The books close, with room to spare, by an overwhelming margin. I mention this partly because there is a predictable misreading waiting here, and it arrives every single time a measurement engine is described in public. The misreading is that this is free energy, that somebody has finally built the machine the patent offices have been rejecting for 200 years, and that the establishment will now bury it. It is worth saying clearly why that is not what is happening, and the reason is not that physicists have declared it impossible by decree. It is that the accounting has been done in detail by people who wanted very much to find a loophole, and the loophole is not there. The energy the engine extracts is real. Its source is fully identified. It is smaller than the energy required to run the apparatus by a factor so large that writing it down feels almost unkind. Any child with a hand crank generates more power than this device, and does not require a machine the size of a car to keep it cold. The demon was never going to win. He was only ever going to teach us where the money goes. Why then does it matter at all? Because the point was never to build a power plant. The point is a change in what counts as a resource. Thermodynamics for 200 years has had two currencies, heat and work. Everything a system can do, it does by trading between those two, and every result in the field is ultimately a statement about the exchange rate. What this line of research establishes is that measurement is a third currency, not a metaphor for one, not a special case of one, a distinct thermodynamic resource with its own accounting that can be converted into work through a defined cycle under stated conditions. That is a change to the structure of a field rather than an addition to its contents, and changes of that kind have a history of mattering far more than they appear to at the time. Carnot's insight was an accounting insight. He did not build a better engine, he worked out what an engine is. Shannon's insight was an accounting insight. He did not build a better telephone, he he worked out what a message is. Neither of them looked, on the day, like the foundation of an industry. And this is not a bolt from nowhere. It has a lineage, and the lineage is what should make you take it seriously. In 2017, Cyril Eluard, Andrew Jordan and colleagues published a proposal in Physical Review Letters for a Maxwell Demon engine in which work is extracted directly from the measurement channel, no hot reservoir required. They showed something else remarkable in passing. In the regime of very frequent measurement, called the Zeno regime after the ancient paradox and formalized by Baidyanath Misra and George Sudarshan in 1977, the erasure cost that Landauer identified can be made to approach zero. The demon's bill, in that corner of parameter space, shrinks toward nothing. In the same year, Nathaniel Cotte, Benjamin Huard and collaborators reported observing a quantum Maxwell demon at work, published in the Proceedings of the National Academy of Sciences. They built it in a superconducting circuit, and they measured the extracted work directly, using power detection resolved at the level of individual microwave photons, while simultaneously tracking the entropy and energy of both the qubit and its cavity, not inferred, measured. The following year, 2018, a paper in Nature Communications reported information-to-work conversion by a Maxwell demon in a superconducting circuit system from a separate group, and work extraction from a transmon qubit acting as an engine's working substance, fueled by measurements that do not commute with the qubit's own energy, has been probed experimentally, with the qubit amplifying a microwave field from which the work is then drawn off. So the measurement engine is not a new idea in 2026. It is a research program roughly a decade old with hardware results behind it. What Garcia Pintos, Liu and Gorshkov add is a general construction, a way of designing the feedback for a continuous engine, with the control Hamiltonian doing the work, and with the arrow reshaping and the engine falling out of the same mathematics. Where does it go? 2 places, and the authors name both. The first is quantum batteries. This is a genuine research field, dating to work by Robert Alicki and Mark Fannis around 2013, concerned with storing energy in quantum states. The interesting claim in that literature is not about capacity but about speed. Under the right conditions, a collection of quantum cells can be charged faster than the same number of independent classical cells because of correlations between them. Small proof-of-concept devices have been built, using organic microcavities and superconducting circuits. A measurement engine is a natural charging mechanism for such a thing, a way of pumping energy into a quantum system on demand, with the feedback loop deciding where it goes. The second is far more mundane and probably more immediately valuable: quantum state preparation. Before a quantum computer can run any algorithm at all, it has to get its qubits into a specified starting configuration, reliably and fast. This is the unglamorous bottleneck of the entire field, and it consumes a substantial fraction of real machine time. A control scheme that can actively steer a monitored system into a target state, rather than waiting for it to settle there, addresses that directly. Which is, when you look at it, exactly what a project called Beyond Moore's Law would be expecting for its money. None of which answers the question that any sensible person asks at this point, which is whether the thing works. Part 12. What would have to happen next? Here is the thing I've been holding back, and it is the single most important sentence in this entire video. Nobody has done it. There is no experiment. There is no chip on which the arrow of time has been reversed. There is no laboratory in which a measurement engine has run a continuous cycle. What exists is a paper, a mathematical construction, worked through carefully, backed by numerical simulation, and published in a good journal after a long and evidently demanding review. That is not nothing. Theoretical results of this kind are how essentially every experiment in quantum physics begins, and a construction that survives 23 months of referees is a construction that has been attacked and held. But simulation is not demonstration, and a proposal is not a result, and if you take one thing away from this video, it should be the ability to hold those apart. So the honest question is not whether they reverse time, it is, what would have to happen for somebody to find out? There are 2 objections that any experimentalist would raise in the first 30 seconds, and the reassuring thing, the genuinely reassuring thing, is that the authors clearly heard both of them before publication. The first objection is feedback delay. The entire scheme depends on acting on information while it is still relevant. The detector registers something, and by the time your control pulse arrives, the system has moved on. If it has moved on far enough, you are correcting for a situation that no longer exists, And your correction is not a correction. It is new disturbance. In current superconducting setups, that round trip, detection, amplification, computation, synthesis, delivery, takes tens to hundreds of nanoseconds. The system, meanwhile, stays coherent for tens to hundreds of microseconds. Divide one by the other, and you get roughly 1,000 to 1 in the experimenter's favour. You have about 1,000 chances to react before the thing you are reacting to has ceased to be quantum. That ratio is the reason this proposal is about superconducting circuits rather than anything else, and it is why the authors say plainly that their intended next step is a demonstration on superconducting qubits, chosen precisely because those systems support rapid feedback and highly efficient detection, and because they have already hosted working quantum versions of Maxwell's daemon. The second objection is detector efficiency. I flagged this earlier, and it is the one that would keep me up at night if this were my experiment. The scheme requires knowing what the measurement did. That knowledge comes from information leaking out of the system and arriving at your detector. Anything that leaks out and does not arrive is information you do not have, and worse, it is information the environment does have, which means the environment is measuring your system in ways you cannot compensate for. At perfect efficiency, you know everything the environment knows and the scheme works cleanly. Below that, you are correcting partially blind, and the question is how gracefully the performance degrades. The best measurement chains today, built around Josephson parametric amplifiers, exceed 50%, and in favourable configurations approach or pass 80%. That is dramatically better than a decade ago, and it is not 100, which brings us to what I think is the most reassuring detail in this whole story, and it is buried in a place almost nobody looks. When the authors revised their preprint in December of 2025, they attached a one-line note explaining what had changed. The note reads, "Updated with simulations of non-ideal measurement regimes." Translated, somebody made us prove this survives imperfect detectors. That is a referee doing their job and authors doing theirs. It means the version of this result that got published is not the version that works only in a fantasy limit, where every photon is caught and every pulse arrives instantly. It is a version that has been tested, at least in simulation, against the conditions a real laboratory would impose. Somebody always pays, and in this case what got paid was 9 months of extra work to close the gap between an elegant idea and a checkable one. There is a reason to be moderately optimistic that somebody will try, and it is that almost none of the required capability has to be invented. Consider what already exists separately in working laboratories. Continuous weak measurement of a superconducting qubit with real-time trajectory reconstruction, routine for over a decade. Real-time feedback fast enough to intervene inside the coherence window, demonstrated at Yale in 2019 on a quantum jump successfully. Quantum Maxwell daemons built in superconducting circuits with directly measured work extraction. Done by at least 2 independent groups in 2017 and 2018. Precise control pulses shaped by optimization algorithms, standard practice in every quantum computing effort on Earth. Every ingredient is on a shelf somewhere. What has not been done is assembling them into this particular arrangement and running the analysis. That is a real amount of work. Probably a couple of years for a good group with a working fridge and a graduate student who wants a thesis. But it is not a moonshot. It is an integration problem, and the groups capable of doing it are not obscure. The laboratories that built the first quantum Maxwell daemons, the ones that caught the quantum jump, and the ones that developed the amplifier chains all still exist, still have the hardware, and have every professional incentive to be first. So what would a real demonstration look like? It would look profoundly unimpressive. A superconducting chip in a refrigerator, continuously monitored, with a feedback loop closing in nanoseconds. Thousands of experimental runs, each lasting microseconds, each producing a measurement record. Then a statistical analysis over all of those records, computing the asymmetry between forward and reverse trajectories, and comparing it against the same analysis with the feedback turned off. The result would be a number. If the number is meaningfully smaller with the feedback on, cancellation works. If it crosses 0 and goes negative, the arrow has been inverted. There would be no visible drama, nothing to film, nothing that looks like anything. 2 plots, side by side, with error bars. And here is what would falsify it. If the asymmetry refuses to cross 0, if it approaches it and then stalls no matter how hard the control field pushes, then something in the construction is wrong, or something about real measurement is not captured by the model, and the interesting question becomes what? If the engine's extracted work comes out at 0 or negative once you account for everything honestly, the thermodynamic half of the claim collapses. Either of those outcomes would be a real result and would tell us something we do not currently know. That is what makes this worth paying attention to rather than worth arguing about. It is checkable. It is checkable soon, on machines that already exist, by named groups in identifiable laboratories, using techniques that are already routine. The verdict on this is a matter of a few years, not a few decades, and it will not require a new collider or a new telescope or a new generation of physicists. Somebody will simply do it, and then we will know. I find that unusually satisfying, and I want to say why, because it is a point about how science actually feels from the inside, as opposed to how it looks in headlines. A great many of the biggest open questions in physics are, at the moment, not answerable. We cannot test most theories of quantum gravity because the energies involved are beyond anything we will build this century. We cannot settle what happened before the Big Bang because the evidence, if it exists, is behind a wall of hot plasma. We cannot determine whether the multiverse is real because almost by construction, we cannot look. Those questions are enormous, and they are stuck, and a certain amount of the noise in popular physics comes from the fact that stuck questions generate speculation indefinitely, and speculation is cheap. This one is not stuck. It sits in the narrow, unglamorous band where a claim is strange enough to matter and small enough to check. Nobody has to wait for a new machine. Nobody has to argue about interpretation. Somebody turns on a refrigerator, runs a few thousand cycles, computes a number, and the number either crosses 0 or it does not. That is the whole scientific method, in a fridge the size of a filing cabinet, on a question about the direction of time, which leaves exactly one thing left to settle. It is the thing I promised at the very beginning of this video, and I have made you wait for it long enough. Part 13. Is this the breakthrough? So, is this the quantum physics breakthrough we have been waiting for? I promised you an answer, and I am going to give you 3, because there are 3 defensible ones, and you have now done enough work to be entitled to all of them. What I am not going to do is pretend that one of them is obviously correct. The first answer is no, and it is probably the majority view among working physicists, and it goes like this. Nothing philosophically new has happened here. Everybody in quantum thermodynamics already understood that the arrow of time in a monitored system is a statistical property of the measurement record. That was not a secret. What this paper contributes is a clever, rigorous, well-constructed piece of control theory, showing how to manipulate that property on purpose, together with a useful spin-off in the form of an engine. It is a good paper. It is a contribution to a specialist field. The word time in the title is doing publicity work that the mathematics does not require, and the thing we are actually waiting for, an account of what time is, remains exactly where it was. On this reading, the honest answer to the question is no, and it was never trying to be. The second answer is possibly yes, but not for the reason anybody said, and it comes from taking the funding line seriously rather than the headline. On this reading, the significant thing is not the arrow at all. It is that measurement has been promoted from a nuisance to a resource. For 2 centuries, thermodynamics has had 2 currencies, heat and work, and every result in the field has been a statement about trading between them. This work, and the decade of experiments behind it, establishes a third, with its own accounting and its own conversion cycle. Structural changes of that kind have a habit of outrunning their announcements. Carnot did not build a better engine. He worked out what an engine is, and the entire industrial world was downstream of that. Shannon did not build a better telephone. He worked out what a message is, and everything you have ever done on a computer is downstream of that. Neither looked, at the time, like the foundation of anything. On this reading, the answer is quite possibly, and you would not be able to tell yet. The third answer is yes, and you will not know for 30 years, and it is a minority position held seriously by a minority of serious people. On this reading, the result is one more entry in a pattern that has been accumulating for a century, and that nobody quite wants to name. Every property we have ever attributed to time on close examination has turned out to be a property of a relationship rather than a property of the universe. Relativity did this to the rate of time. There is no universal tick, only clocks in relation to observers. This work, and the experimental program around it, appears to be doing the same thing to the direction of time, turning it from a feature of reality into a feature of the relationship between a system and whatever is keeping records of it. If that pattern holds, and it is a pattern, not a proof, then the eventual account of what time is will be relational rather than absolute, and this paper will be a small brick in a large wall that nobody alive will see finished. You do not have to choose between these. I do not think I have chosen. What you should not do is mistake the third for the first. Take a speculative reading that its own holders label as speculative and present it as the thing that was demonstrated. That confusion is the entire mechanism by which a careful paper becomes a headline about time flowing backward. And the disagreement here is genuinely unresolved, in a way that goes beyond this one result. Carlo Rovelli has spent a career arguing that time is emergent in the way temperature is emergent, and his point about temperature is worth holding on to. Temperature does not exist for a single molecule. Ask what the temperature of one atom is, and the question is malformed. Temperature is a property that appears when you have enough things and start averaging, and yet nobody thinks temperature is fake, or an illusion, or unimportant. It will still burn you. Lee Smolin, who helped to build the same theory of quantum gravity as Rovelli and read the same evidence, reached the opposite conclusion. Smolin argues that time is the one thing that cannot be emergent, because the laws themselves must have a history in which to have become what they are, and history requires time to be fundamental rather than derived. Two physicists, one collaboration, identical data, incompatible conclusions. That is where the field actually is, and anyone who tells you otherwise is tidying, and I want to defend that state of affairs rather than apologize for it, because there is a habit of treating unresolved disagreement as a failure, as though a field that cannot answer its central question is a field doing badly. It is the opposite. Two people who work together for years, who trust each other's competence completely, who have access to precisely the same evidence, and who come out at incompatible positions. That is what a genuinely hard question looks like from the inside. If the answer were available in the data, they would both have found it. The disagreement is not noise sitting on top of the science. It is a measurement of how deep the question goes. There is one more thing worth saying about Rovelli's temperature comparison, because it diffuses the objection almost everyone raises at this point. When people hear that time might be emergent, they hear that time might be an illusion, and they reasonably object that their life does not feel like an illusion. But emergent has never meant fake. Pressure is emergent. It is just molecules hitting things, and pressure will crush a submarine. Sound is emergent, and sound can shatter glass. Temperature is emergent, and temperature will kill you in either direction. Every one of those is a property that does not exist at the level of the individual parts, and is entirely real at the level where you live. If time turns out to be emergent in that sense, nothing about your Tuesday changes. The thing you are experiencing remains exactly as real as it was. What changes is where you have to look to find out what it is made of. But here is the part I keep coming back to, and it is the reason I wanted to spend this long with you on a paper about control theory. You're also a system that keeps records. Your sense that time moves forward is not a perception of some external current flowing past you. There is no such current. We looked for it for 300 years and never found it in any equation. What you have instead is an asymmetry in your own memory. You have records of what happened and none of what will. That asymmetry is what forward feels like from the inside, and it is the whole of what forward feels like. And those records are physical. They are patterns in matter, written by processes that obey thermodynamics, at a cost measured in joules. Every memory you have was paid for. Every one you have lost was overwritten, and the overwriting warmed the room by 3 times 10 to the minus 21 joules a bit, and that entry is in the ledger of the universe permanently and cannot be removed. Which means the thing that feels like the deepest fact about being alive, that there is a past behind you and a future in front and they are different in kind, is the same category of thing as the asymmetry in that measurement log. Not the same scale, not remotely the same complexity, the same category. I do not find that diminishing, and I have thought about why. I think it is because the alternative was never as good as it sounds. If time's direction were a fundamental law, a cosmic current carrying everything one way whether it liked it or not, then you would be cargo. You would be a thing the current happens to. Whereas if the direction is a property of records and you are the one keeping them, then the forward you experience is not something being done to you. It is something you are participating in, continuously, at a cost, in joules, every second you are awake. That is a smaller universe and a larger role in it. Somebody just took a system small enough to control, found where its direction of time was kept, and turned it around. You are not that system, and you never will be. The arithmetic makes certain of that more thoroughly than any law could. But you are made of the same stuff, running the same accounts, paying the same bill. The universe does not know which way is forward. I said that a long time ago tonight, standing in front of a cup that would not stop falling, and it was a fact about physics then, and slightly disorienting and easy enough to set down. It is not a fact about physics. It is a fact about the difference between you and everything else in the room. The universe does not know which way is forward. You do. And the entire difference between those two sentences, the whole of it, the past and the future, and the fact that you can tell them apart, costs about 3 times 10 to the minus 21 joules a bit. So was this the breakthrough we have been waiting for? I think the honest answer is that it depends on what we thought we were waiting for. If it was a machine that gives things back, then no, and nothing ever will be. If it was a small group of people quietly discovering that the most permanent seeming feature of reality is a property of the accounts, and that the accounts can be kept differently, then it may have arrived in February in a journal, under a title nobody read carefully, and we spent the summer arguing about the wrong sentence.